Welcome back to ECE 320A. In this video, what I would like to do is talk about what you were asked to do in quiz 4.1, which was to try to find governing equations connected with or associated with this particular RLC circuit. And what I want to do now is try to give you some hints or help relative to that particular question or request in quiz 4.1. One thing that we can start to think about when you're confronted with finding differential equations or governing equations of RLC circuits is to just inspect the circuit itself and try to find how many energy storage elements are in the circuit. And we know that the inductor stores energy in its magnetic field. We know the capacitor stores energy in its electric field. The resistor doesn't store any energy. That's an instantaneous relationship between voltage and current. The voltage and current relationships on L and C, however, do have this time connection by means of a first-order derivative relating the current and voltage in the inductor and capacitor, and that's what gives them this introduction of dynamics into your system of equations. When we're asked to find then governing differential equations or governing equations, what we want to do is initially just inspect, as I had said, the circuit and find out how many energy storage devices or elements, and that will generically, sometimes there's some cancellations involved if we have a series combination of capacitors or something like that. But assuming that all of the energy storage devices can be considered linearly independent in the circuit, then two energy storage devices, in this case we have one capacitor and one inductor, that tells us something about what's going on. And in particular, it tells us that we can expect either, let's say, a second order differential equation or we could be content or satisfied with two first order, and these first order differential equations generally would be coupled. But with two energy storage devices, we're expecting a second order differential equation in one variable or two first order differential equations in two variables that are going to be what we will call state variables, or variables that contain the information about the dynamics of our system. And the other thing that you need to keep in mind until you retire, which I keep going over and over, is this Eli and ice relationship. Eli is for the inductor, ice is for a capacitor, and that now gives us a way of remembering this differential relationship between current and voltage. For the inductor, it's V sub L is equal to L di sub L dt. That's the relationship between the current and voltage of an inductor. And for the capacitor, ice tells us that we now have I, the current through the capacitor induced in the capacitor, I sub C of t is equal to C dV sub C dt. And what we will do then relative to those particular relationships, or falling back on Eli and ice, we can now say, oh, we need to concentrate on the inductor current or the capacitor voltage, or both of those, when we're confronted with inductors and capacitors in our circuit. It's really this differential quantity that tells us, oh, I sub L of t is changing with time, or that's now our inductor current, which is one of our state variables that we might want to focus on. So the variables to focus on are the state variables, which are these variables that actually are present in these differential relationships. So we have the inductor current and we have the capacitor voltage. When we're writing our differential equations, then we want to be thinking about writing these equations in terms of inductor currents and capacitor voltages. With that said, what we need to now focus on is how can we find differential equations that contain only the inductor current, and in this case, and capacitor voltage and their derivatives, along with the excitation signal or waveform V of t. That's the voltage source in this particular circuit. The V of t is an independent variable that will be occurring or appearing in our differential equations. We expect that to be there, but the other things that we expect are only inductor currents and its derivatives and capacitor voltages and the derivative or derivatives of the capacitor voltage. And if we look at this particular circuit, now we're trying to find equations that govern the dynamic behavior. It's a mesh, and a lot of times students get very comfortable or fall back on trying to do mesh analysis, which is reasonable. So let's see what happens when we write KVL for this particular circuit, and I can write it in terms of the excitation voltage, V of t, and the three remaining voltages, the voltage dropped across the inductor, resistor, and capacitor. Note in the way that I have this color-coded that the state variables or the variables of interest are actually the inductor current in red, I sub L of t, and the capacitor voltage, V sub C of t. But to begin with, let's just write down some equations that are actually true or valid. And the first one that we can write down is a KVL equation, and this is around the single mesh. And that says that we have minus V of t. Let's start in the lower left-hand corner, and we go up through the negative terminal of our voltage supply. Then we hit the positive sign of our inductor voltage. We hit the positive sign of our resistor voltage, and we hit the positive sign as we've defined them of our capacitor voltage. And those then come in with the respective polarities that we've assigned, plus V sub L of t, plus V sub R of t, plus V sub C of t. And that brings us back to where we started. The algebraic sum then of those voltage drops or rises, however you want to think about it, but it's the algebraic sum. We need to keep track of the signs that we've identified with those particular elements is now given by this equation. And this could be a true equation. This is a true equation, but now it contains three unknowns and one known. V of t is known, and it has three unknowns, V sub L, V sub R, and V sub C. And we want to now see if we can rewrite this in terms of the state variables, which are V sub C of t, so we can leave that particular variable alone. We have our excitation signal, V of t, we can leave that alone, but now it would be nice to rewrite V sub L and V sub R in terms of the inductor current or the capacitor voltage and their derivatives. And now, since we haven't yet retired, we have Eli to fall back on, which gives us a way to rewrite the drop across that inductor, or the voltage drop across the inductor, in terms of the inductor current. Or from Eli, we can now replace V sub L of t with L di sub L of t dt. And that's now one of our state variables that we were interested in. V sub R of t, we can now rely on hopefully something also that we keep in mind until we retire, which is Ohm's law, and that's just R times the current through that resistor, which in this case is the same current through the inductor, and so that we can replace V sub R with R I sub L. That now is what we want, because now we have the state variables I sub L and its derivatives, and V sub C and its derivatives, only those variables, and the excitation signal V of t. That allows us then to write one differential relationship, and that's minus V of t plus L di sub L of t dt plus R I sub L of t plus V sub C of t is equal to 0. In this particular case, we have one differential, or here's a first order differential equation. We actually said we needed two first order differential equations or one second order. So we aren't quite finished, but this is now one first order, and you can see that it's actually coupled. We have both state variables involved in this equation. We have I sub L and V sub C, so I could say one first order coupled differential equation. And now we need to try to find another one. Well, we've written a KVL. We only have a single mesh. There are really no more KVL equations to write, but we can maybe realize that we can relate or connect the inductor current with the capacitor current. It's the same current flowing through this entire circuit, but now remember we can use ICE to rewrite I sub C in terms of the capacitor voltage. Let's then write a KCL equation at the right top node. And doing that says that we now have I sub L of t. That's one of our state variables. That's what we want. And that's the same as I sub C of t. Or if we go back to this highlighted node in the upper top right corner, we can see that I sub L is coming into that node and I sub C is leaving. So I sub L in, the sum of the currents in, equal the sum of the currents out. And that's now consistent with this equation. But we don't want I sub C, we want V sub C, and that now is available to us by remembering ICE, or now we know that I sub C of t is just C dV sub C dt. And if we now combine those two, if we combine that or replace I sub C with its differential relationship in terms of the capacitor voltage, we see that we have I sub L of t is C dV sub C dt. And this now is another first order, and it's coupled. We've coupled now the inductor current with the capacitor voltage differential equation. And we could stop then with double star and star for our governing equations. Those are true equations. They're coupled, and we could just be finished with that particular analysis. If we wanted to come up with a single second order differential equation, we can actually combine the first equation and the second equation, star and double star, to end up with, starting on the left, we have minus V of t plus L but now we're going to replace everywhere we see I sub L of t, we're going to replace it with c dv sub c dt. So now here we have L di sub L dt, which says that we now have L d by dt of I sub L, but I sub L is now c dv sub c dt. And then the c is constant, that can be slid out, and we now have this second derivative of v sub c. Back to the start equation, we have plus r I sub L, that we said we were getting rid of I sub L, which is c dv sub c of t dt, since I sub L is the same as I sub c, or I sub L is equal to c dv sub c dt. And now we have one more, which is plus v sub c of t equaling 0. And this is now our second order differential equation that is true for that RLC circuit. And this now gives us a second order differential equation in terms of our capacitor voltage, where we now have minus v of t plus LC v sub c double prime of t plus RC v sub c prime of t plus v sub c of t is equal to 0. And there is our single second order differential equation, and that also is a true dynamic relationship or a true governing differential equation associated with that series RLC circuit. So we could either say that we have this way of connecting or describing the dynamics, or we have the combination of double star and star, and those two coupled first order differential equations are equivalent to this second order single differential equation.